Okay, last time we were talking about the density based clustering method to group the data, where clustering is an unsupervised learning approach. So basically the task here is to find group of uh, nodes in the graph, group of nodes in the graph which are connected or which are densely connected. And as I told you last time, that the density of a graph ranges between 0 and 1, right? So for example, this is a graph which has let us say 3 nodes and there is no edge between them, so its density is 0. Okay, let me write it so that you better not confuse it with the node. So here the density of this graph is 0. Alternatively, for example, I have another graph, the blue graph, where again I have 3 nodes and every node, each node is connected, directly connected with the other node. So here the density of the graph is 1, right. So the ranges of density of the graph vary between 0 and 1, right. So the goal here is to extract such dense groups of nodes, we can call them subgraphs within a bigger graph, whose density is larger than a given threshold, right. For example, if you see here, this is a group. Here the goal, this is a visualization of a portion of a graph where the graph represents the PPI, protein interaction network, and the clusters which are extracted here, all of them have a density greater than 0.6, right. So this we were talking last time. So the goal, or rather let me jump to the point where I left the discussion. So the goal of density based clustering is to extract homogeneous groups, we can call it clusters or groups, whatever. So the data will be presented using an adjacency matrix, and we will be having number of nodes as an input to the input to the algorithm sorry, and the number of edges and the density is computed in this manner, which I discussed last time. For example, density of a graph of a given graph is the number of edges multiplied by 2 divided by number of nodes into number of nodes minus 1. So this gives us the density, right. But for this particular algorithm, the density based clustering algorithm, our input will not be just the adjacency matrix, but we will give a threshold density as well. This is the threshold which we will be using to extract groups or clusters from a graph. And then there is another density. This is also this CP cluster property density also ranges between 0 and 1, and it is used within the algorithm when we reach that particular step. So I will be explaining its utility. Now the algorithm basically starts with a single node as a cluster and grows the cluster by adding nodes from neighbors one by one, right. For example, here if it selects this node as a cluster, then it will try to, maybe it will select this node to be added to the cluster, then maybe this node to be added to the cluster, and then this node, and this selection is guided by a certain mechanism, and I'll be explaining it shortly. So this growth which I demonstrated to you, this growth of the cluster in this manner is is continued unless and until this extracted clusters density is greater than a certain threshold, right? And now if for example here the smaller clusters can also be extracted, but the size of the clusters, for example, this is a very small cluster with 2 nodes, and if we see here, this is another cluster, relatively bigger cluster. This itself, this is a bigger cluster, right? So the size and shape of the cluster in this particular algorithm is dictated or governed by 2 things. One is this threshold density, and the other one is the connectivity connectivity within the graph itself, right? So as long as the extracted cluster has the density greater than or equal to this threshold, the cluster will keep on growing. But once the cluster density decreases, then this particular threshold, we will stop growing that particular cluster and we will extract the cluster, right? So right. Now, so algorithm starts by growing, adding nodes from neighbors one by one, and it continues expanding cluster as long as following 2 conditions are true. The density of the cluster is greater than the threshold density, and the node in the nodes are in the periphery or the neighborhood of the cluster, right? So once these 2 conditions stop being satisfied, then what we will do, we will remove the cluster from the complete graph, and then we will apply this same process on the remaining graph, right? So but it's not that simple, there are many details into that. For example, once this cluster has been has stopped growing because the density has maybe is fine for this particular cluster, if you see here, but if you further grow it, you cannot see any connectivity between this subgraph and the other nodes in the graph. So what we will do, we will extract this cluster, we will remove this cluster from the graph, and in the remaining graph we will start clustering again, maybe from this point or maybe from this point, right? So this process will continue. But there are certain important questions in this. For example, if you see here, it says that start with a single node as a cluster, right? So the algorithm starts with a single node as a cluster. However, when you see this complete graph, now the question is from which particular node you have to start clustering, right? This is a very important question. So before going into the detail of the starting node to grow the cluster, we need to learn a few concepts. Right. The first concept is the weight of an edge, right? Usually in a graph, now let me make it for you. Usually in the graph we have these nodes, right? And when these nodes are connected with each other, for example, this is a graph, right? These edges have either weight available in the data set, right? Either these weights are available in the data set, and what we do, we usually put, let's say 2 here, which will be available in the data set. Maybe here it's 3, it's 4, and maybe it's 6 here, right? So this is the weight of the edge. Or at times when we don't have weights available in the data set, but there is an edge between 2 nodes, so the availability of an edge is indicated by 1, and absence of an edge, for example here there is no edge, so this is indicated by 0, right? So I hope all of you know about adjacency matrix. Now for example, this is node A, this is node B, and this is node C. So to store it in the memory, we will have a 2 by 2 matrix A, B, C, A, B, C, and A is connected with C and B here. So A is connected with C and B, and B is connected with A, that's all. B is connected with A, and C is also connected with A only. So this is the mechanism through which we store the graph in the memory. This is called adjacency matrix. Alternatively, we have another option which is called adjacency list, but I am sure that you have studied these concepts in the course of data structures during your bachelor's degree. Now, but the weight of an edge which is used here is not is after explaining everything, I am telling you that it's not like this, right? Right. The weight of an edge is computed differently here in the density based clustering, right? Now, the weight of an edge u comma v is the number of common neighbors of nodes u and v, right? So let me demonstrate it visually to you. Okay, for example, this is a node. Let me try to make a complex graph, not a complex graph, but maybe a bigger graph. Okay, this is efficient, this is sufficient. Now let us connect these nodes through edges, right? Okay, let me number these nodes as well. For example, let's call it, okay, A, B, C, D, E, F, and G, right? So let us pick any edge, and here this let us pick this edge, and let us call this edge B comma E, right? Now I have to find the weight of this particular edge. So I have to see that how many nodes in the graph are such that these nodes are neighbors of both B and E, right? Now if we see, node A is connected with E, and node A is connected with B as well, right? So there is one neighbor, one common neighbor. Now if I see that node C, it is connected with B and it is connected with E as well, right? So plus 1. And if I see F is connected with E, but F is not connected with B. Okay, let me change the graph to facilitate this example. So now if I make a connection like this, now here F is connected with E and F is connected with B as well. So right, okay, and then D is also connected with E, it's not connected with B. So we will skip that, and G is not connected with either of B and E. So if we see here, this sums up to 3. So the weight of this particular edge, which is between which is between B and E, will be 3, right? Similarly, we will be computing the weight of other edges as well, right? So basically, what this 3 indicates, this 3 basically indicates the strength of the connection between B and E, because they have this much, like this much number of common friends, right? So this shows the strength of connection between B and E, right? So here the weight of the edge is denoted by the number of is represented by the number of common neighbors between U and V, right? So the example which I showed you, that was a visual example, but in real time processing, you need not to see each and every node like that, because at the end of the day you will be having an adjacency matrix, right? It will be a matrix like this. For example, you have node A, B, C and D, so it will be like, right? And the diagonal, this diagonal will have zeros, because there will be no edge between A and A, B and B, C and C, and D and D, because we assume that there are no loops within the graph, right? So how can we find the weight of the edges of the complete graph? That is simple. You simply do what? You simply take the square of the adjacency matrix, right? So this will give you the number of common neighbors of the nodes for example, you have this adjacency matrix, you make another copy. By square, I do not mean that you take a square of the value which is placed here. No, it's not like this. You make it's basically matrix multiplication, right? So you will be having you make two copies of the adjacency matrix, and what you do, you multiply these two copies with each other. The resultant copy will be a new matrix, right? A, B, C, D, A, B, C, D, and whatever this value is here, that will show the weight of the edge between node A and node D after computing M square, right? So that will be a very quick method to compute weights of the edge, right? Now next is the concept of the weights of the nodes, right? So once you have computed the weights of the edges, for example, let me make another graph here, right? Okay, this is enough. For example, okay, let me label them as well, A, B, C and D. Now the weight of this edge, it has only one, A and B only has one common neighbor, so this way its weight will be 1. Similarly, its weight will be 1, only one common neighbor, its weight will be 1. And if we see here, they have these C and D, how many common neighbors do they have? They have 0 common neighbors, right? So its weight will be 0, right? Now the next task is to compute the weight of the nodes, right? Now the weights, computing weights of the node is simple. Now if you see how many edges are incident or touching node B, this edge and this edge, right? Now if I see here, this edge has no weight 1 and this has weight 1 as well, so I will add simply add these two, it will become 2. So the weight of this node will be 2. Similarly, there are 2 edges incident on this node A, so sum of these 2 edges, weights of these 2 edges is 2. Same goes for this as well, because here although there are 3 edges incident on node C, but if we see here, this is 1, this is 1 and this is 0, right? So the weight here is 2. And now if we see here, there is only one edge incident on this node D, but the weight of the edge is 0, so the weight of this node becomes 0, right? So the weight of the node is sum of the weights of the edges incident on that particular node, right? Now the weight of the node is sum of the edges connected. I am using the term incident, you can call it connected to the node. The weight of every node is calculated, right? So what we do, so once now if you have got the concept of the weight of the edge and the weight of the node, now once we cannot obtain the weight of the node unless and until we have not computed the weights of the edges, right? Now once we have computed the weights of the edges, we get the weights of the nodes, and among the weights of the node we can identify which node has the highest weight, right? We can identify that which node has the highest weight. Maybe there are more than one nodes, 4, 5, 6 or multiple nodes having the same highest weight. So what we do, we start growing the cluster from the node having the highest weight, and if we have more than one nodes with the same highest weight, we can pick any one, right? So this is how we will be choosing our starting point to grow the cluster, right? Okay. Now the next task is to generate is generating neighbors. For example, once okay, let me use this graph. Once, for example, we have decided that okay, this is the starting node. Now the next task will be to generate all neighbors. Now this is sort of simple. The neighbors of this cluster, if you see here at present in this cluster, this pink cluster, there is only one node. So all the nodes which are connected to this particular node will be neighbors of this pink cluster, right? So so all the connected individuals with this node will be generated as neighbors of this pink cluster, right? Then what okay, let me go to that step and make sure that I don't miss anything. Okay. Now the neighbors of the cluster are nodes connected to any node of the cluster but not part of the cluster, right? But if you see here, for example, okay, let me use color pink. For example, this, so everyone which is connected to this pink node is the neighbor. But for example, let's assume that this node also becomes part of the cluster. How? I'll be telling you, but let's assume it happens. Then every node which is connected to either this node or this node, right? Either node, let me label them, either node A or either node B. So any node which is connected to either of these will be neighbor of the complete cluster, right? But since these two A and B are also connected with themselves, but they are already within the cluster, so we cannot say that A is neighbor of cluster B because both are within the same cluster, right? Okay. Now once we have generated the neighbors of the cluster, the next task is that among so many neighbors of the cluster, which node is to be added to the cluster, right? So this is determined based upon two measures. You can opt for any of the measure, or maybe you can sum up both the measure, but these two measures are recommended. The first one is the sum of the weights of the edges between a neighbor and the cluster, or the number of edges between a neighbor and the cluster, right? Let me demonstrate it here. Now, for example, this node is added to a cluster. Now, all these other nodes are neighbors of the cluster. So one choice is that we pick a node to be added to the cluster which has the maximum number of connections between this cluster, this pink cluster, and the neighbor under consideration. But here, since this cluster has only one node at present, so there is a chance that there may not be multiple connections. But if I assume that the cluster has now two nodes, so if you see here, this particular neighbor has connection with this node of the cluster and this node of the cluster as well, right? So either you decide based upon the number of edges which are between the neighbor and the cluster, or what you do is, for example, each edge has weight. The weight of the edges will be computed as I mentioned earlier. For example, this has weight 2 and this has weight 3. So what we will be doing, that we will be summing up these weights, and for example this node has different sum of weights of the edges, and this has different. Whosoever has the highest sum of the weights of edges between the node and the cluster will be added to the cluster, right? So among these two criteria, you need to choose only one, but this criteria number 1 seems to be more logical, but it's up to you. You can use the second one as well. Now, sorry. The neighboring nodes are then sorted on any one of the criteria which I told earlier, and then the one having the largest value will be added to the cluster. Now, before adding a node to the cluster, we need to make sure these two things. One, once we add the node in the cluster, the density of the cluster should be above the threshold, right? Secondly, we need to check whether the node is part of the cluster or part of its periphery. Now this task is to be computed using this property, right? For example, what we will be doing, we will be computing this CP. Now CP is computed as the number of edges between the cluster. For example, this is the cluster, and okay, for example, this is the neighbor to be considered, right? This is connected with these. So the red one is the cluster, and the green one is the candidate to be added to the cluster, right? So this E is this is EC. This is the number of edges between the node and the cluster. Now here this will be equal to 2, right, divided by density, which is of course density of this cluster, and multiply by number of nodes within this cluster, which is 3, right. So this, whatever the result of this this equation is, it should be greater than this threshold which was initially given as input to the algorithm, right. Okay. Now this is how this is how we keep on. Once both of these conditions are satisfied, so the node will be added to the cluster, and the next process will be to generate neighbors again and sort them, and then check these two properties, and the cluster will continue growing, right. Right, this is basically this is redundant from the, for example, whatever is mentioned here basically explained here as well. So now once once we have once the condition, such condition occurs that I am trying to find an example here. Once such condition for example here, for example, this got added to the cluster, this got added to cluster, this got added to the cluster, and this got added to cluster, right. Now if we further generate neighbors of this cluster, there are no more neighbors. So what we will do, we will extract this cluster, we will remove it from the graph, and in the remaining graph we will start clustering again, right. But here this is condition 1, and for example for another cluster, this node got added to the cluster, this got added to the cluster, and this got added to the cluster, right. But again there are nodes which are neighbors to this cluster, because this node is connected with this one and this one as well. But by adding these nodes, the density of the cluster goes below the threshold density. So again in this case as well, we will be stop growing the cluster, and we will extract it from the graph, right. And in the remaining graph we will be executing the algorithm once again, right. So this is how this algorithm works. So this is the flowchart of this algorithm, which I have explained in detail. Then there is a concept of overlapping cluster. For example, where some parts of the clusters are also parts of other cluster as well. For example, this is a cluster, red cluster, and then this is a blue cluster. So if you see here, red and blue cluster are totally disjoint. But let's say if I make a pink cluster, so which is like this, so certain parts of the red cluster and pink cluster are common, they are overlapping, right. If you want to customize our algorithm to extract overlapping clusters as well, so what we need to do is, once the cluster starts growing, Let me demonstrate it visually. Once the cluster stops growing, right, what we will do, we will mark the cluster, we may store the cluster, but we will not extract it from the graph, right. So in this way we can identify or extract overlapping clusters using density based clustering as well, right. So I hope and the flow chart of this density based cluster to extract overlapping cluster is mentioned here. So it may be not in a very good resolution, but I'll be emailing you the slides, so there you would be able to see it in a clearer format, right. So thank you.